So now let's discuss about another conic section. So we have the parabola. This is where a plane intersects a cone, going through the edge of the cone and cutting down the base of the section, rather than across to the other side of the cone like with circles and ellipses. We learned quite a bit about parabolas earlier when we first learned how to graph functions, but let's learn the rigid definition. A parabola is the set of all points that are equidistant from a fixed point called the focus and a fixed line called the directrix. In other words, any point on this curve will be just as far from the focus as it is from this directrix at its closest point. This is different from something like an ellipse, where it's the sum of the distance from the two foci that remains constant. We also know that parabola as our second degree polynomials, but we only look at very simple example like x squared and other in vertex form that involve only no transformation of x squared. But if we have something trickier like negative x squared minus 2x plus 1, with this standard form, we can readily identify shapes or stretches that can be applied to a similar function. Instead, we can do one of two things. We can either rearrange the equation to get it into vertex form, or we can follow a series of steps that will allow us to figure out where the vertex is, and other information that will allow us to graph the function. Let's try the first way first. Remember when we learned how to complete a square? That's exactly what we're going to do here, so that we can get this parabola in vertex form. Because once in vertex form, we can just identify all the transformations we need to apply to a simple x squared curve to get this particular parabola. Let's discuss how to do this to a generalized version of a parabola first. Remember, from ax squared plus bx plus c, we want to get it into this form where we have a out here, x minus h inside parentheses, which is then squared, and then k out here. A, h, and k will then represent terms that stretch and shift the parabola so that it's easy to graph. The first thing we need to do to get closer to this form is to factor and a out of the first terms. For ax squared, we just lose the a, but for bx, we end up with b over a times x. Then we compile the square. We complete the square. Remember to do that. We take this term here, cut it in half, and then squared it. That gives us b squared over 4a squared. We add that inside the parenthetical term, but we must realize that really adding a times this term since a is multiplying across this sum, which means we also have to subtract b squared over 4a elsewhere in the expression, so that we don't change the value of the expression. When this trinomial is a perfect square, which was the point of all this, so we express it as x plus b over 2a quantity squared. Now if we express this term as x minus negative b over 2a, we have this precisely in vertex form for a parabola. We have an h, an a key, k, which will allow us to find the vertex, and we have a stretch value over here. Let's take our particular parabola and use the A, B, and C values to evaluate h and k, which will give us negative 1 and 2 as the x and y coordinate of the vertex, respectively. Beyond this, A is negative 1, which means that the parabola opens downwards, and that's how we take a parabola in standard form and put it into vertex form so that it's easily to graph. Of course, we don't have to derive this equation we can just complete their square regularly with numbers. We just factor A out of the first two terms, complete the square, being careful to compensate for the coefficient, change this form. Now, let's try the other way we mentioned, where we leave the equation as it is. The first step in this algorithm will be to figure out whether the parabola opens upward or downwards. To do this, we look at A and see if it is positive or negative. If the coefficient is positive, it opens up. If negative, it opens down. In this case, we can take the coefficient as being negative 1, so it opens down. The next step is to find the vertex. As we said, this will have an x-coordinate equal to negative b over 2a, which in this case is equal to the negative of negative 2 over 2 times negative 1, which all comes out the negative 1. Once we have that, we can play it into the function to get the corresponding y value, which in this case will be 2. This confirms that the vertex is at the point negative 1, 2. From here, we could get additional points by finding the x and y intercepts. The x-intercept are the point where the function is equal to 0. So we can find them by setting the function equals to 0. In this particular case, in order to solve this, we have to use the quadratic formula. Otherwise, we just plug in all the coefficients and we get the answers. We can just evaluate these 2 to the nearest 10 so that we can get approximate value to graph. The y-intercept will be much easier to get because that is the value of the function when x equals 0, or the point where the function across the y-axis. We plug in 0 and we should get 1. Lastly, we could find the axis of symmetry, which will be x equals negative b over 2a, just to make sure everything looks right. So now we have the vertex, some intercepts and a line, and that's all we really need to generate a reasonable sketch of this function. We now have a variety of ways to graph parabolas, and not just the easily kind. We can graph parabolas in vertex form by applying transformation, or we can even graph parabolas in standard form by completing the square or finding serious points on the curve. So, that's all for this video.